will use your you will find your moment now. So where the dot is, right? This is where we are going to take our reference for our moment. Or this is where we're going to take our moment. So summation about moment in the z-axis as a function of x is equal to 0. So omega naught L over 6 is going to go into clockwise. So it's equal to minus omega naught L over 6x, right? And then you have plus by omega naught x squared over 2L, right? And this will be x over 3, right? And then you have plus by m as a function of x is equal to 0. So from here, your expression will be m as a function of x is equal to minus omega naught x cubed over 6L. Omega naught x cubed over 6L. I bring over minus and plus by omega naught L over 6x. And then now you let this whole equation equal to EI d squared y over dx squared. Okay, so if you look at our integration using just purely integration method, our moment, okay, so this is our moment equation. So m as a function of x is equal to minus omega naught x cubed over 6L plus by C1x plus by C2. Okay, so this was our equation number 2, right? So we realize that it's still the same, okay, both expressions. So you see where I highlight, okay, this expression and this expression are the same, okay, these two expressions are the same. And then the C1, right, we already found as omega naught L over 6 is the same. And then C2, we know that it's equal to 0. Then from here, okay, if you use the positive shear, positive bending moment, then from here, right, the steps onwards, okay, so the steps onwards, so the next steps onwards is exactly the same from here. You just start to integrate again. Okay, so equation number 3 and 4 will be the same. You apply the boundary condition and so on and so forth. So if you are going to use the positive shear and positive bending moment technique, you have to find what? You have to find, right? You have to find what? You have to find the reaction force at point A. If you use the integration method, okay, if you use the integration method, all you need to know is your boundary condition, and you don't need to find your what? Your reaction. Okay, so it has advantages and it also has disadvantages. Again, the integration method has to be used if the distributed load is very complex. Okay, like when I say complex, it looks like this. Okay, you cannot find the distance of your equivalent load. Okay, so that is one example.
Can't we use series to find it? But wouldn't it be like Fourier series and stuff? But it would take long.
Yeah, no, just use integration method. If there are A, B, and C in the beam, should we have two boundary conditions? Yes. Okay, the boundary condition will not be the same. Okay, that's what someone asked. Okay, now I'm going to do another example. Okay, so this example number 4. Yeah, so far so good, right? This is pretty straightforward. It's just integrate here, integrate here, integrate here, integrate here, right? So we are going to look at another example. Okay, so example number 4. Okay, so example number 4. Example number 4 is like the most useful method for using elastic curve and also the integration method. Okay, this is really useful. Okay, right. So example number 4. This example is statically indeterminate. Right? So like what we have learned before, remember we started solving statically indeterminate structure, right? We not only look at the reaction force, but we also look at the what? Deflection. This is what we're going to do. Okay, same thing. We're going to incorporate the reaction force and the deflection for determine in statically indeterminate structure. Okay, now can you all realize something now? Okay, can you all realize something? So now we are, next week is the last week of the lecture, right? So when we started using elastic curve, right? When we started using elastic curve now, right? What is a factor that we don't need to assume anymore? Can anyone answer that question, please? Before using the elastic curve, we used to make an assumption, right? And what is this assumption? This is in lecture number 1 or lecture number 2. What was the assumption that we make? Anyone? Can you all remember? We used to what? I'm going to write in a different color. We used to assume that A or that member, anyone, member.
That's rigid.
Yes, who are you? Where are you?
Sean.
Sean, thank you. When A to B is a what? Right? Like what I promised you. Later on in the chapter, is this a rigid body anymore? No more. Yes or no? We don't need to make that assumption anymore, isn't it? Right? We can determine the deflection now as a slope now or as a function now. Okay, that's the beauty of this technique. Okay, that's the beauty of this technique, right? So we don't need to make that assumption anymore. Okay, now you come to full circle. Not quite full circle yet, but close. Okay, let's look at this example over here. Okay, so this example, okay, is a built-in, right? So it's a built-in, and then again we have I always use triangular load because a rectangular load is very simple. Okay, triangular load is more complex. I want you to get used to it. Right? So this is omega naught. This is point A. This is point B. And then at point B, we have an extra support. That is totally not necessary. Okay. So now we want to find, okay, now we want to find the reaction at point B. Okay, now we want to find the reaction at point B. So we know that over here, this structure is statically indeterminate. We know that. Okay. So how this structure will deform, right? How this structure will deform, the structure will deform this way. Right, the structure will deform this way. Okay. Oh, yeah. Not really wellly drawn. Not happy with it. Okay. So this is how the structure is going to deform. Okay. So now we have x is equal to 0 and x is equal to what? L. Okay. So this is V M theta y. Now you understand why I make you memorize Vm theta y, right? So V you integrate, you get M you integrate with elastic curve, you get theta you integrate, you get what? y. That's why I think it's for last week I made you try to remember this sequence already. Okay, Vm theta y. So at x equal to 0, v is what I don't know, m is what I don't know, but I know theta is equal to 0, and I know that this y is equal to 0. Okay. Over on the other side, we know that m is equal to 0, right? Because when I remove the support at A, B will rotate, and y will equal be 0. Okay. And y at x equal to 0, theta is equal to 0. So if you see, if I draw a chain line, right, at this point over here, where it's in green now, the slope is equal to 0. Okay, the slope is equal to 0. And I'll try to, so I don't want you to memorize this also. Okay, I memorizing is something that will not work at all. Okay, so can you all see me on the screen? Yes or no? Right?
Yes.
Yep.
Okay, so you can watch where my hand is, right? Where my hand is holding the ruler now. So now this is the cantilever end. Okay, then I push my finger on the other side. I push it downwards. Can you see that? Right, where my hand is gripping the ruler, the slope down here is equal to 0. Can you see that? Okay, so that's how I want you all to remember your boundary condition. Okay, by physically doing an example as simple as this, not memorizing. Okay, if you memorize it, good luck. You know why? Because after my course, you will forget everything. Okay, so not worth memorizing. Okay, now I lost my pen. Okay, so now we know why theta is equal to 0 over here. Okay, so I'm going to use positive shear and positive bending moment for this. Okay, I'm going to use, I want to, and later on I will tell you why integration will not work. Okay, later on. Okay, so I'm going to show you using positive shear. Okay, using positive shear and positive bending moment. Okay, so we know the equation of the distributed load. So for this case, it is equal to omega as a function of x is equal to omega naught L over x as a multiplied by x. Okay, so we want to find the equation of the equivalent load. Okay, so omega EQ, which is equivalent. So we integrate omega naught x over L dx 0 to x. So this is equal to omega naught x squared over 2L. Okay, so when x is equal to L, the equivalent load will be equal to omega naught L squared over 2L. This is equal to omega naught L divided by 2. Okay, so from here, right, so we have this equation now. We can now construct our free body diagram. Okay, we can construct a free body diagram now. So from here, so this is our point A, our point B, right? So we have a load coming down here, right? So this is equal to omega naught L divided by